Hi there, welcome back to another Study With Me session. My name is Amy. I'm the headmaster tutor at Pinnacle Coaching College. So today what I've got for you is a topic on rates of change. So this topic is sort of dealing with sort of one of the major application areas in calculus. There are both 2-unit and extension components in this particular module, so we'll look at examples in both areas. Let's get straight into it. All right, so a lot of these questions are actually exam questions, which I've kind of had to pick and choose to suit, I guess, the level of knowledge of our Year 11 students. Usually this topic is pushed back into Year 12 in the old syllabus where you've learned the derivative of all the different functions as well as how to integrate functions. So we're not going to be able to look at the integration side of the rates of change concept because at this stage I think most people wouldn't know how to integrate yet or haven't done that at school. We're just going to focus on the derivative side. Now, in a nutshell, right? I know the concept of physics, the concept of rates of change scares a lot of students. But if you start kind of remove that fear that, oh my God, it's physics, it's something physical, how I'm gonna, map all that out, it doesn't make sense in my head. It really doesn't matter. Just know rates of change is the derivative. That's it. Okay, whenever the question is asking for a rate of change, you're looking for the first derivative. And in fact, remember what the derivative is. It is to do with the gradient of a function. Yeah, gradient is the rate at which y changes over the rate at, actually, it's the rate at which y changes with respect to x. That's essentially what it is, okay? So don't need to overthink it. If you see rate of change, write the derivative. That's all you're looking for. So let's have a look at this question here. We have an equation that model the volume of a tank. We're given that initially there are 3,600 liters of water drains from the bottom of the tank. It takes 60 minutes to empty the tank. And we're given the equation under which this volume is sort of decreasing under. So what is the volume? What volume does the model predict will remain after 10 minutes? So basically, if you know the time, you should be able to find the volume because that's what the model predicts. So all you have to do in the first part is sub in t is equals to 10 minutes, right? And then you just put that straight into your calculator. That's 2,500 liters. That's it. All right, so then the second part, at what rate does the model predict the water will drain from the tank after 20 minutes? So we're after t is 20 and we're after rate. So remember, rate means derivative. So that's all we're going to do. So we're going to differentiate that with respect to time once using the chain rule. Okay, so bring the power down. Subtract the power by 1 times the derivative of the inside, which is just the derivative of that thing. All right, so simplify that. So we've got minus 3600 times 2 over 60. All right, so that number, if you just put that into the calculator, is minus 120. And what I might do, I'll simplify this a little bit further as well. All right, so that's the equation. So at 20 minutes, t is equal to 20. The rate is equals to minus 120 plus 2 times 20, which is negative 80. And it's liters per minute, right? It's volume on time. So at that point in time, you're losing 80 liters every minute. That's all it's saying. Right? Very simple, right? And the last part, at what time does the model predict the water will drain from the tank at the fastest rate? Now, to understand that, I think it's important we look at the rate equation, which is this guy here, and actually look at this on the graph. So I'm just going to draw the rate equation. It's a linear function, so it's very easy to draw. But I'm having trouble drawing a straight line. There we go. Alright, so you can see that when t is equal to 0, dv dt is minus 120. And it only goes to 60 minutes anyway. So if you sub in t is 60, dv dt goes to 0 if you sub it in. Okay? So that's what the function looks like for the rate. So you can see that the rate starts off at negative 120 and then it goes up and up and up and up until it goes to 0. So in answering the third part, if you look at this question, right, if you focus on the rate equation, which is minus 120 plus 2t, you might not be able to gather what is the largest, fastest rate, right? But you can look at this, okay, what is the fastest rate? Minus 120, right? It's losing at 120 liters per minute as opposed to, I guess, 20 minutes later. I mean, I might put that in for your reference. 20 minutes later, you're losing only 80, and then this rate is actually dropping, right? So that's pretty much the answer. So fastest rate is minus 120. It's just the highest rate you can see in the graph of it. All right, so I hope that makes sense for you. Let's have a look at next one. So remember that relationship between derivative and gradient. All right, so that's what we're going to look at in this particular question. So it goes, the graph shows the level of pollutants in the atmosphere over the past 50 years. So you can see that it goes from 1945 to 1995. So describe briefly how the level of this pollutant has changed over time. And include a mention of the rate. Okay, so first of all, just talk about the level of pollution, right? It has definitely gone up, right? Probably at least double, just assuming this thing is to scale, but it's probably not. We'll just mention that the level of pollutant has increased. But let's talk about the rate. What the rate is to do with the gradient, right? So if I draw a tangent at this point, let's draw it at another point. Let's draw this at another point. You can see the blue lines, right? It's steep, less steep, less steep. So the rate it's actually is decreasing. Okay, so it's not increasing as quickly, in other words. So the way to word that is that so the level of pollutant has increased, but at a decreasing rate. So what would an increasing rate actually look like? Let's talk about this. It will look something like this. Right, like an exponential function. So you can see this is the opposite, right? So the gradient at this point is like this, very flat, and then it gets steep, and then steeper. Okay, so you can see that it is increasing and an increasing rate. So that's all it is. Remember, rate, it's gradient. All right, so a very specific application of rates of change is motion, right? Motion meaning displacement, velocity, acceleration. Essentially, it's a very, very simple calculus relationship. So I'll just very quickly mention this. If you've got displacement time, so x is often used to represent displacement in mathematics, a little bit different to how the physics course is written. If you want to get the velocity, you differentiate. So v is dx dt. And to go from velocity to acceleration, you differentiate again. That's pretty much it, okay? So in other words, velocity is the rate at which displacement changes, right? It's the rate of change for the displacement. Acceleration is the rate at which velocity changes. That's all it is. All right, so answering this question, find the initial displacement. Initial usually means t is 0, displacement is x, so we just sub it into the question. Alright, so you get minus 3 on 4 meters. Alright, so the minus in this particular question is an indication of the direction. So usually, I mean, in this context where it's not really defined too much how it's moving, let's say the origin is here, it just means you are on the left. Yeah, you're on the left of the origin. Yeah, negative 3/4. Alright, so find the velocity of the particle when it passes through the origin. Alright, so first we're going to have to find the velocity function first. So taking the displacement time function, remember velocity is the rate at which the displacement changes, so you need to differentiate that. Chain rule. That's pretty much it. And you know how I feel about negative indices, so let's change that back with that. Okay, so that's your velocity time function. All right, so as it passes through the origin, so we need to figure out the time when it passes through the origin. So origin is when x is 0. So we're going to solve this to 0 to try to figure out when it passes through the origin. So it passes through at 3 seconds. All right, so therefore, that's the velocity, 1 on 7 meters per second. The fact that it's positive means it's traveling towards the right. That's all it means. I show that the acceleration is always negative. So just going back, right? Acceleration is the derivative of the velocity. So we're going to take the velocity expression. So I'm just going to take it at this point there. Yeah, so it's just easier for us to differentiate. I'm going to do a derivative again. Alright, so it's important you explain why this is always negative. Yeah, it's not just because of the minus 14, it's also because t plus 4 itself is always going to be greater than 0 for t is positive, right? Time is always positive in these questions, so as long as t is greater than or equal to 0, this thing is going to be above 0. So basically you have a negative number divided by a positive number, so that means your acceleration, so actually I'll just label that acceleration just so that there is less confusion around that. Okay, so therefore acceleration is negative for as long as t is positive. Okay, and then the last part is the sketch. So we're trying to sketch this function here. Now this is a hyperbola, so I might take this opportunity to review hyperbola with you. So first thing is t cannot equal to -4. because it will make the denominator go to 0. So if I was to draw this thing, there should be a vertical asymptote at -4, but not that we're going to draw all the way there, right? I just want to comment on it first. Now, and then the 1 means it got shifted up by 1, so there is a horizontal asymptote at 1. In any case, this is a little calculator trick I teach all my students. If you're looking for horizontal asymptote, what you're studying is as t approaches infinity, where's your function going? So if you put t is like 10,000, not 10,000, that's too small, like 10 million or something, yeah, or 10 to the power of 6, 10 to the power of 9, you just sub it in, right? You'll find that your calculator is going to tell you it's going to approach 1. So actually, I'm just going to show you, right? So 1 over 1 minus 7, 10, 6 plus 4. All right, so you can see that that's what I'm putting into the calculator. I'm going to hit equal. You can see that it's almost 1, right? If I put power 9, that should actually be at 1. Let's see. Yeah. So you see, if I put the power high enough, our power 12 is 1. Okay, so that's a little trick to tell where the horizontal asymptote is. Okay, so we've got 1. Is the horizontal asymptotes. Now, we know that initially, let's go back to the question. Initially, it started at -3 on 4. So, -3 on 4. And it's 0 at 3 seconds. So if I was to draw this entire thing, right, entire branch, it will kind of look like that, right? It's a hyperbola. There would be another branch up here, which I won't talk about, but we're only drawing for t is greater than or equal to 0. All right, so that's the function, all right? So just kind of chopped off a hyperbola and draw the bit you need. And that's all it is. So all the different parts also is framed as finding the velocity, finding acceleration or whatever. It helps you kind of piece the puzzle together, be able to draw this function. And I always say to my students, right, I find that drawing functions stump a lot of students, but your fallback method is plot the points, right? If you're like spending 5 minutes and going nowhere, just start plotting the points. Like, why are you wasting time, right? If time is precious in an exam, just start plotting the points and kind of guess what it's going to look like. So that's all I've got to say on that one, the little tip from me. Moving on. All right, so another type of equation we work with a lot under rates of change is an exponential rates. So a lot of physical phenomena actually follows exponential growth and decay, and that's what this kind of explores. So in this question, now actually before we dive in, so generally speaking, let's say this equation, right? Generally speaking, that number in front of your exponential function is your initial value. Now, how do I know? If you put t equals 0 in there, you will find that it is 200. So that's the initial value. All right, so in this case, we are given that population of insects is growing exponentially according to this equation. T is weeks after insects are first counted. At the end of 3 weeks, population has doubled. So when t is equals to 3, n is equals to 2 times the original amount, 400, it has doubled. All right, so that's all it is. All right, so subbing it into the equation, right? So 400 and t is 3. So divide the 200 across. I'm just going to do it over here. So k is log E2 on 3, which is about, now, log E2 on your calculator is ln2, right? So that's what you type in, ln2 divided by 3. Okay, so that's what you type into the calculator. I'm trying to minimize the reflection. There we go. Yeah, which is about 0.2310. Okay. Now, usually I like to use the exact answer rather than the rounded answer, only because the calculator can be quite sensitive when it comes to exponential function. Just even 4 decimal place, it can be like a couple of numbers off. So second part, how many insects, let's see, how many insects will there be after 12 weeks? So you need t equals 12. What is n? Alright, so our equation for n currently looks like this, EKT, where k is this guy, or I will use this guy as an exact answer. So I'll just write it as ln2 on 3t. Okay, so just sub in 12. And then you can just put that straight into your calculator, and actually it comes out very nicely, 3,200 insects. Now, what I also recommend a lot of students do, you can use the memory function as well to store the k value, so you don't have to put in such a cumbersome expression into your indices. All right, so next one. At what rate is the population increasing after 3 weeks? So rate means derivative. So I'm going to take this guy. Now I'm going to leave it as k for now, just to keep things a little bit simpler. So dn dt is 200 times the derivative of that is k-e-k-t. Basically, the derivative of the power goes in front times whatever the exponential function is. That's all it is. Okay, so at 3 weeks. So I'm going to put in the different k values. So ln2 on 3, ln2 on 3 at 3 weeks. So t is 3. Put that into your calculator, it should come out as 92.4. That's pretty much it. So to keep your answer exact, try to use the exact value of k. If you use rounded, maybe rounded to at least 4 or 5 decimal places. You should get very close. I think I did it yesterday and it came out at 3198. So you're like 2 insects off. Ideally, just use the memory function and then you don't have to run into these issues at all. Right, so that's a pretty basic one just to draw out what is exponential growth, how do you find that k, and then what's the rate, how do you find rate. All right, so the harder example is where, like this guy here, you're given a relationship rather than actual value. So you're just given Q is equals to QO E minus KT. So QO is usually your initial amount, and it tells you that in the question anyways. So you can see that we don't ever know what QO is, but we know that Q is equals to a half QO when T is 1690. So you do it the same way we did the previous when you sub that information in. Okay, so you put 1690 in place of T. Now you'll find that the QO on both sides, you can just cancel them out. It's irrelevant. And then log both sides. So K is equal to log a half, or basically ln a half. Now this time I might write the decimal form just to make things a little bit easier. Zero 0.0004. Alright, so then second part. After how many years does 20% of the initial amount remain? So in other words, you want to find time when Q is equal to 20% of the initial amount. Okay, so right now our equation is like this, E minus KT, where K is 0.0004. Yeah, that's it. Okay, all right, so we're going to sub this in. You'll find that again, QO is irrelevant, they cancel out. And then log it. All right, and then just divide that number across. So put that into your calculator. You should get about 3924 years. And that's pretty much it. So hopefully that all makes sense. If you look at the working, it's actually very similar to the previous exercise. It's just you'd never know what the initial amount is, QO, but essentially it's irrelevant as long as you know, I guess, the relationships, right? When it's double is that, when it's 20% is that sort of thing. All right. So that pretty much draws us to an end on the sort of the 2-unit type of questions. So if you're a 2-unit student, you probably can stop this video at this point, and if you want to go back and have a look at the examples again, feel free to do that. Now there's a couple more questions I want to show my extension students. One area is related rates. So this is a more advanced application of rates of change where it uses the chain rule to sort of bring together variables and try to do some advanced calculations with that. So we'll take a look at a typical example in this area. So we've got grains that's been poured at a constant rate of 0.5 cubic meters per second. So imagine grains are going in, going into the pile at 0.5 meters cubed per second. Now, this is a little trick I always teach my students, especially if you're like physics, science, it's completely out of my head, I don't like them. There's a very neat trick to determine what this is, because this is a volume time measure. This is dV dt. Yeah, that's how you work out what this thing is. Okay, so it forms a conical pile with an apex angle of 60 degrees. So 60 degrees. The height is h, the base is r. So that is the case. Okay, so first of all, if I cut out that triangle, right? If the apex angle is 60, half of it is 30. So I can see that H and R has a tan relationship. So tan 30 is equal to R on H. So that's 1 on root 3 is R on H. So R is equal to times the H across H on root 3. That's it. Yeah, simple as that. All right, so the second part, we want to show the volume. So the volume is of a cone. Now this is a little neat trick. The volume of anything pointy, which is a cone and pyramids, always a third of the prism. So for a cone, it's a third of a cylinder. So a third pi r square h. Now you can see it doesn't match the equation yet because I still need to replace r. Yeah, because we've worked out r, so it's h on root 3, stick that in. So that's pi on 9h cubed. Alright, so the third part is the actual core of the related rate stuff. Hence, find the rate at which the height is increasing. What that is saying is go look for the dt for me when that h is 3. Okay, so first, in any of these type of rates of change question, obviously, unless you actually have the height time expression, you won't be able to find the dt by differentiation. You need to calculate from your other rates, right? So we use chain rule to break this up into a connecting expression with dv. Now, there's a reason why we use dv in this case. So dv dt, we actually know dv dt is 0.5. Okay, so this thing is 0.5. This thing means you need a HV or VH expression, which we've got VH expression. So you just need to differentiate it and you'll get to it. All right, so you see how why dV is a quick link here? Mainly because you've got dV dt. And the second thing is you can actually do dV dH as well. All right, so we're going to take V is pi on 9h cubed, dV dH, differentiate it, pi on 3h squared. Okay, all right, so that means the HdV is the reciprocal, yeah, it's the flip of this guy here. So 3 on pi h squared times 0.5. All right, so then from here, we find the rate at h equals to 3, so actually sub in 3. So that should be 1 on 6 pi. That's it. So you can leave it exact like what I've done here, meters per second, I assume. Let me see. Yeah, per second. Okay, or you can actually also shove it into the calculator and just round it off, which is about 0.053 meters per second. So it means that as you pour that grain into the cone, right? As you pour that grain into the cone at 0.5 centimeters, sorry, it wasn't centimeters, it was meters cubed per second, your height is growing at 0.05 meters per second. Yeah, so as you increase the volume of this, the height of this cone is growing at that rate. That's what that rate means. All right, so hopefully that makes sense. So to summarize, the main thing is when finding a related rate like this one here, you are looking for components, or in this case, somewhere to link your expressions together so you can use the information you've got, which is dV dt and dH dV. That's pretty much all it is. So as long as you can figure out what that link is, and then you just like go into shopping, I need a bit of apples, I need a bit of pears, and shove it in the blender, it goes and it comes out all right. That's all it is. Very simple, right? All right, last one. Just a harder exponential rate question and sort of also demonstrating Newton's law of cooling. Basically, what Newton's law of cooling says is very simple, right? The rate at which your thing cools down, or in this case, I think we're heating it up, yeah, but same idea. It's always proportional to that difference between the temperature of that thing, in this case the turkey, and your surrounding temperature, in this case the oven, right? Or just think back, if you have a cup of boiling water, right? It's always going to cool down to your room temperature, right? It's never going to go to 0 degrees unless you're in the fridge or something, right? So the idea is the rate at which that cools down is always going to be proportional to that difference between your temperature of your boiling water and the environment or the room temperature. That's what it is. So in the first instance, okay, let's have a read of the question first. We've got a turkey that's been taken out of the refrigerator at 5 degrees, placed into a 190 degrees oven. So that's the environment temperature. So we're going to show this equation satisfy the rate as well as satisfy that initial temperature. Okay, so see how we do that. So let's start with the initial condition first. So T is 0, putting 0 in there. So you can see it's 5. Okay, so it satisfies condition. Okay, the rate. So now we actually have to try to differentiate this and show that it follows that equation. So dt, d little t, 0. Now I'm just going to reshuffle this a little bit. Alright, so that times that is positive 185k, which I've just moved the k in front. Now the reason being, to be able to prove that expression, you need to take this expression, yeah? And make 185 e to the power of minus k the subject. So if you move that to that side and the t to the right side, it's 190 minus t. Okay, so that's what we're going to shove into here. All right, that's pretty much it. If you compare this, they're not exactly the same thing yet, so just take out the negative and that swaps the numbers. Okay, so therefore it satisfies the differential equation. Alright, sorry, the writing's a little bit ugly there, but that's pretty much it. Okay, moving on. So now actually doing some calculations with that. So at 9 a.m., it's shoved into the oven, so that's t equals 0. At 10 a.m., 1 hour later, it's 29. Okay, so that's going to help us figure out the k value. So let's copy, or I'm going to copy for you the equation first. Alright, so sub it in, right? When t is equals to 1, temperature is 29. And then moving things around. Alright, so the difference between that is 161 divided 185 across, so minus k is log that. So remember that's ln. Put that into the calculator, it's about 0.13895. Alright, so we found the k value. Now the question is, when it's cooked at 80, right? So we need to find out when that happens. So subbing it into the same equation, so this one here, I'm just going to leave the k as a k, yeah, and then we'll put in the k last. So we're trying to solve for the power, so let's move things around. Over minus k, and k is 0.13895. Okay, so put that into the calculator. It should come out as about 3.74 hours. Now make sure you answer in the context of the time and to the nearest minute. So add that to 9. You should get, therefore, the turkey cooks at 12:44 p.m. Yeah, so if you don't know how to play with time, it's actually very simple on the calculator. So all you do is take 9 and plus 3.74. Okay, so normally your calculator will display something like that, right? So 9 plus 3.74 is a fraction I've got there. Then you hit the bubble button. So this button over here. Let's see if you can see it. Okay, so this button over here. And then you can see that it's been displayed as 1244. Yeah, that's it. That's how you figure out. You press that bubble button or the degree button, that's what it's called. Yeah, it turns things into degrees and minutes. It's very useful for time as well because time works in the same way. All right, so that's pretty much it on a slightly more advanced question. Hopefully that all makes sense to you. Now remember, I think this whole module is meant to be a revision module. I'm going through, I think, exam questions in this area, which I feel that it's very common, or there's a little bit of trick around it. I'll often also do those as well. And the best way you can benefit from these videos is have a go at doing these exercises yourself. Then look through my explanation and see if you missed anything or if there's anything you can learn from my process. So that's pretty much it. So that's all I wanted to say. Hopefully you found this helpful. This is rates of change module. It can be quite difficult for a lot of students, just trying to make that leap between more theoretical calculations into more practical applications. Some students absolutely love it because I think, there's more meat to the bone, right? You're not applying stuff in a vacuum. If you have any questions, comments, you would like me to work on certain topics, just let me know and leave a comment down below. You can reach out to us in the various ways on this slide you can see there. Best of luck for prelim exams. Bye for now.